Do you think our species and AI would be friends? What you see here are patterns hidden in speech waveforms that we humans use to communicate. Species. Ishi, ishi, ishi. So the same pattern repeats for the fricative phoneme sh, having the vowel phoneme e as its left and right context. These patterns are output of an algorithm we've developed called Travellingwave Filter Bank, TFB for short. Its signal processing is inspired by the traveling wave on the basilar membrane in the human ear's cochlea. In this video, I'll talk about what these patterns are and how they'll help us build voice bots with human-like performance and efficiency. First, let's compare these patterns with current state-of-the-art in speech processing. So the spectrogram on top displays energy of speech spectrum as a function of time and frequency. Apart from high-frequency energy, it fails to yield patterns specific to the sh phoneme. In contrast, the TFB output displayed at the bottom reveals an entire set of what we call as modulation patterns. Obviously, TFB is far more superior to the spectrogram, but the big question is, what do we do with these modulations? So for over 100 years, we've been building models for machines to recognize spoken words. We haven't paused a bit to think, wait a minute, we humans do not recognize words directly. We recognize phonemes followed by syllables, words, sentences, and meaning in that order. So instead of jumping on the same bandwagon, we thought, why not examine the TFB output more carefully? Maybe there is some kind of correlation between the modulations and phonemes. It turns out that just like the synchrony in music produces sounds mapped to symbolic notes, the synchrony in modulations trace symbols that map phonemes. Here I've shown an acoustic symbol for each she that reveals several interesting patterns. For example, notice in the bottom left figure that when the amplitude modulation A4 shown in blue rises up, A1 shown in red drops down, and vice versa. Also, the maximum gap between A4 and A1 for sh is greater than 20 dB. Also for sh, A2, A3, and A4 are grouped closely together and far away from A1. Next, in the bottom right figure, observe that F1 and B1 rise in the sh region, and the voiceless fricative sh has no pitch, whereas its adjacent voiced E vowels do have pitch. Next, let's see how this acoustic symbol may be written as a set of mathematical equations that machines could use for reasoning. Here I've written down some simple equations called the acoustic code to model the shape of the Ishi symbol we just saw. For example, equation 1 tells you that the A4 minus A1, which is the gap we talked about, is greater than a threshold. Equation 2 models the symbol's shape when A2, A3, and A4 are closely grouped together and far away from A1, and so on. A point to note here is that unlike the 2D spectrogram we saw at the beginning of this video, this acoustic code is machine readable. Now, why is this such a big deal? Well, many legendary scientists have long argued that just like the human genetic code, there must be a speech code that lets us robustly hear phonemes, even when the word it represents is unknown, even when they're spoken with accents, and even in the presence of noise. So we've derived acoustic symbols and codes like the ones you just saw for each she for all English language phonemes. We've called it Speech Code 1.0, and its design details are as follows. So there are about 32 phonemes in American English. What we've seen is that each phoneme has 1 to 6 symbols depending on its adjoining context. So if you do the math, less than 192 symbols are needed to uniquely map all phonemes. Also, as shown here, you can simply alter just one bit of the equation and create a very different sounding phoneme. And finally, notice that the code equations are derived using acoustic phonetic reasoning. They're not learned from data. Only their thresholds are fine-tuned using very small amounts of data, minimalistic data. We call this reasoning AI. I recently presented these results at the world's topmost AI conference in speech, and a link to my paper is in the description box below. So now I'm going to say something speculative. Think about it. In just 4 kilohertz cell phone bandwidth, we human beings interact with each other using acoustic symbols and codes. We add new symbols to create languages. We alter these symbols just a little bit to create accents. Now, because these symbols and codes are so unique, we essentially end up filtering out unwanted noise like fan, air conditioner, background music, high frequency sounds while driving a car, and so on. Now, what if a dog bark or a dolphin's whistle or a bird's chirp What if they all have similar acoustic symbols buried in their sounds that we do not understand, but they use them to communicate robustly in the same 4,000 hertz bandwidth? To me, that's fascinating, and to me, that points to some form of intelligence behind nature's creation, the coding mechanism. So we built an engine around reasoning AI called the TFB engine, and here are some of its applications. First, TFB can be used to build acoustic models that are robust to mismatch arising due to variations in accents, noise, use of unknown words, and so on. Second, using TFB, systems can provide intelligent feedback for 100% task completion. For example, let's say a user spoke a sentence, generative AI has no common sense, and Google AI displayed general AI has now common sense with pretty much zero feedback. Now, if Google AI was integrated with TFB, then the output will additionally include markers that highlight where the errors happen, word confidence scores, wrong pronunciations, wrongly stressed syllables, etc. Finally, TFB will help significantly lower costs associated with speech data collection, model training, model tuning, and GPU-based expensive servers. So TFB engine is a tiny piece of technology, but if it's integrated right with, say, an Alexa-powered Chat GPT or iPhone Siri-powered, I don't know, like an Apple GPT, we're talking about the power of generative AI and the common sense of reasoning AI coming together to create an all-pervasive conversational UX that'll let you not only chat with your machines, but also argue and reason with them as if they're your best friends. Yeah, I mean, that's pretty much it. That's pretty much it. So, hey, thanks a lot for watching this video. Merry Christmas and good luck for 2024.